All right, let's get started. For lab 2 today, we are going to learn buffer preparation and pH measurements. So why do we need buffer? Buffer is pretty important, especially in a biochemical lab, because most biochemical reactions are actually happen in a specific pH. Because as you know, in human body, uh, most of the biochemical reactions are actually catalyzed by an enzyme. Um, so enzyme requires specific pH to achieve its maximum efficiency activity. So pH is very important. Ideally, our uh, circular system. So the blood in our body is actually, you can treat your blood as a buffer system. So it will maintain the pH of the blood, um, which is quite important to people. So basically, what we are going to do today, experimentalize, we are going to use uh, phosphate salt. We are using two phosphate salt. One is potassium phosphate dibasic. The other one is uh, potassium phosphate monobasic. So we are using um, these two reagents plus some strong acid, which is hydroxyl chloride, and some strong base, which is sodium hydroxide, hydroxide, to make buffer. So we are using these guys to make. We are using three different ways, three different methods to make a same buffer. So how do we? Uh, but before we go into the experimental detail, we are going to know some like basic concepts, some basic equations, which is very important and helpful in today's lab. So before that, let me share my screen so you guys can. I will just go through the handout very quick. So can you guys see my screen?
Yes.
Okay, so basically, I will just go through this handout pretty quick with you guys. So first of all, is the introduction, which is uh, not quite important. I mean, it's important, it's good to know, but so the key concept for today is actually this equation. So how do we how do we define pH? Basically, the pH, actually pH, the definition for pH is the uh, minus log of the concentration of proton in a solution. We can express this in a different way, which is this one. So S equals to pKa plus log the concentration of the conjugated base over weak acid. So what is this? What are those? So if you look at this equation here, this one is just a very simple equation describing how the weak acid is the dissociation of weak acid in a solution. So basically, the weak acid will dissociate and generate proton and the conjugate base. So you can also call this weak base. This is weak acid. This is weak base. So in today's case, the weak acid we are using today is the potassium phosphate monobasic, and the conjugate base is uh, potassium phosphate dibasic. Okay, so Ka is the equilibrium constant, which is calculated by the concentration of proton times the concentration of the conjugate base, then divided by the concentration of weak acid. So when we say this concentration, the concentration is not the initial concentration. So the concentration is when this when this equation goes to the balance point. So they are since this is a reversible reaction. So when the reaction speed from the left to right equals to the reaction speed from the right side to left, when they goes to this state, we call this a balanced state. So when they goes to the balanced state, so at that point, the concentration of proton. So this is the concentration we are using. This is the concentration we are using in this equation. So that's the balance. When they come to the equilibrium state, we are using the concentration of this component to calculate the Ka value, which is the equilibrium constant. So if we go back to from here to here, so this is a Ka, but what pKa is minus log 10 of Ka. So this is how to define pKa. So the pH value the equation we can use to calculate the pH value is pKa plus log 10 over the concentration of conjugated base over concentration of weak acid. Okay, that's for the concentration. That's for the equations. Okay, any questions with this? Pretty clear. This is pretty important because we are going to use this equation to calculate many stuff today. So for today's lab, we are going to use, like I said, we are going to use 3 different methods to calculate, to make the buffer. So I think most of you guys have already read this handout, and you may see 3 pK values for the phosphate acid. Okay, so you may be confused about why we have 3 different pK value, and why we are using 7.2 as the pKa. Okay, so the explanation is actually here. Let me grab this on my laptop and show you guys here. So why do we have 3 Ka values? So if you look at the phosphate acid, okay, the formula of phosphate acid is H3PO4, okay, so which means we have 3 proton in the phosphate acid. So that's why they have 3 equations of dissociation. So the first one, you have H3PO4, then you get a proton plus H2PO4 minus. So this equation, this reaction will have a Ka value, which we say this is K1. And after that, H2PO4 minus will keep dissociation in the solution, which gives you the second reaction, which is if you don't have the potassium here, it will be H2PO4 minus goes to proton plus HPO4 2 minus. That will gives you the equilibrium constant K2 here. So for the third one, and then this one will keep going. It will be HPO4 2 minus goes to proton plus PO4 3 minus. So this is the third reaction that will gives you the constant pK3. Okay, so the reaction, so that's why the phosphate acid will have 3 dissociation constant. But the problem is we are using this. We only use this one as our in today's lab. So that's why the pK value for the pKa value today we are using is 7.2. So no matter which method you are using, you will use the pK value will be consistent. The pK value will be consistent, which is 7.2. Okay. Am I clear here? All right. So for today's lab, we are going to make a buffer. And so before we start, I think I can erase off this. Oh, no, I don't think so. Here, this is the requirement of today's buffer. So number one, the assigned pH you are making is 7.3. So which means we want you guys to make a phosphate buffer that pH value is 7.3. Okay, and the concentration of the buffer will be 0.1 molar. So 0.1 molar is 0.1 mole per liter. Okay, and the volume you are making for today's buffer is 50 mil, 50 milliliter, and like I said, the pKa value you are using is 7.2. Okay, so that's the factors I provide to you before. You guys need to use these factors to determine how to make the buffers. So, like I said, we are going to use 3 different ways to make the buffer. So number one, the method one is using weak acid plus strong base to make the buffer. The second way is similar, but we are using weak base plus strong acid to make the buffer. So the third one is you are using the weak acid and weak base together to make the buffer. So that's three different methods. So let's go through it one by one. Number one, your method one, you are using weak acid and strong base. So I'm not sure if you guys can see here on the top. Okay. So on the top, it shows you guys the method one, the weak acid and strong base. So before we start, we know we are using weak acid, which today is the potassium phosphate monobasic, which is your weak acid. So by using weak acid and strong base to make the buffer, theoretically, you just need to calculate the value of these 2 components you need to add into the buffer, into the beaker. So number one, how much of the weak acid we need? Like I said, we are making, this is very straightforward because I told you guys we are making 0.1 molar buffer, okay? So that means you have already know the concentration. The concentration equals to 0.1 molar, okay? And the volume is 50 mil. So you know the volume, which is 50 milliliter, which equals to 0.05 liter, okay? So if you know concentration, you know volume, which means you can calculate N, which equals to concentration times volume, which will give you 0.005 mole. Okay, can everybody follow this? Okay, so by knowing that, we are, so why do we need this? Because I'm not giving you guys the stock solution for the strong base or weak acid or weak base. I will provide you guys the powder for this. That's why you need to calculate N. And by knowing the molecular weight, you can calculate the mass equals to N times molecular weight, which is actually somewhere on the whiteboard over here. But by knowing the concentration, by knowing the N and the molecular weight, you can calculate the mass you need. So it's some gram over here. Okay, so now we solve the first problem. How much potassium phosphate monobasic we need? So basically, by knowing this number, you just measure this amount of grams of the powder of this weak acid powder on a balance and pour this powder into the beaker. So that's the first step. So now we understand, we know how much of this we need to add. Okay. So for the second part, how much of potassium sodium hydroxide we need? This is sort of complicated, but it's not that hard. So if we write this equation to the right side of the equation, which will give you HPO4 minus. So this one will be your conjugate base, which is weak base here. Okay. So we don't initially if it goes to this equation over here. This is the equation we are using to measure, to calculate the pH. Okay. So pH equals to pKa plus log the concentration of the weak base over the concentration of weak acid. So if we plug whatever we have in this equation, so the pH we are assigned is 7.3, and the pKa value is 7.2. So which means by inserting these two numbers, we can get this equation. So which is log. So this part equals to 0.1. Okay. So with this equation, we can't get the specific number of the concentration of weak base and weak acid, but we can know the ratio for this. Okay. So by knowing this, what we can get is the concentration of weak base over the concentration of weak acid is 1.225. So it's an approximate number, but you can calculate by yourself with the calculator. So how can we know this exact number for these two numbers? So don't forget we have another known element, which is here. The concentration of the buffer is 0.1 molar. So which means the concentration of weak acid plus the concentration of the weak base should be equal to 0.1, which gives us another equation. This equation, 0.0 molar equals to the sum of these concentrations. Okay, so by knowing these two equations, we can easily calculate the specific number of the concentration of weak acid, weak base, and weak acid. Okay, so why do we need this number? That is very important because this is actually we are calculating the final concentration of both weak acid and weak base in the equilibrium state. This is very useful because when we are calculating for method 1, we know this already. We don't know this. We don't know the number of the strong base we need to add. So actually, the concentration of the strong base you need to add is actually equal to the final concentration of the weak base. Okay, so think about it. if we, for example, if we produced, let's say five units. If we produce the final concentration of weak base is 5 units, which means you have to consume 5 units of the strong base. You need to consume this amount of strong base to generate this amount of weak base. Okay, does that make sense? Because the ratio of each component is 1 to 1 to 1 in this equation. So which means you consume you produce this much, you consume this much. So that means you just need this amount of strong base. So if you go back to this part, which means you calculate the concentration of weak base, which is here, that will give you how much you need of the strong base. So the strong base you need initially equals to the strong base, the concentration of the weak base. So that's basically how you calculate this part. So with that being said, you know how much of the weak acid you need to add, you know how much strong base you need to add. The next step for making a buffer is you mix these two components together, and you add water, bring the volume to 50 ml, and that's it. That's for method 1, how to make this. Okay. So method 2 is similar with method 1. The only difference is you are using weak base plus strong acid to make the buffer. So it's quite similar, but the difference is we are using potassium phosphate dibasic, which HCl, to make potassium dibasic. So same thing here. For this, you calculate how much of this you need is similar with this one. You use 0.1 molar times 50 ml. Then you get the n. It's not divided by n, but by doing this, you got n over here, and use n times molecular weight of this one, and it will give you the mass. So similar, very similar with the first method. So still, you need to know how much of the HCl you need to add into the solution. So the HCl actually similar here, and the concentration of HCl needed is equal to the final concentration of weak acid, which is HA here. So you just plug the result you got from here into here, and that will be equal to the concentration of HCl. Then you can understand, you can know how much of HCl you need. Okay, so method 1 and method 2, they are similar things. So if you know this, you should be able to do this. So the third one is you use weak base plus weak acid. Basically you make this by adding weak acid and weak base together. So that will be more straightforward because you have already know the final concentration of A and HA. So by doing this, you just use the final concentration of weak acid times the volume. That will give you the N for HA. Then times the molecular weight of HA. That will give you the mass. So same thing for the weak base. You use the weak base times the volume, which is 50 ml. That will give you the N. Let's say this is N1, this is N2. This is the molecular weight 1. Then times the molecular weight 2. That will give you mass 2. This is mass 2, this is mass 1. So this is pretty straightforward. You basically get the concentration from this equation, then you plug this number into these equations, then you get the exact number, the exact mass for each component. And after that, you just weight this specific amount of weak base and weak acid, mix them together, add water, bring the volume to 50, and that's basically how you make the buffer with the third method. Okay, I know this one sounds like, the calculation sounds like confusing, but I think when you guys actually start to perform work on the calculation, it should be more make more sense to you. So before I let the in-person students start any questions, I will film him for sure and give you more explanation when he do the calculations. So, but before that, any questions?
Can you go back down to where you were calculating like from pH and pKa? Because
Okay.
you went from like I can't see it because of the camera. But you went from
Is that clear? Better?
yeah. You went from acid equals 1.25 base to
Yes.
0.1 equals 1.25 base plus base, and I don't understand where the second base came from.
Oh, you mean here, right?
Yeah, can you tilt the camera a little more down though? Thank you.
You mean this one?
Yes, thank you.
So basically from, are you guys clear with this equation? You get the ratio of weak base over weak acid.
Yeah.
This should be clear, right? So think about if you move HA from the bottom to the right side, what you will have? What you will get? You will get the concentration of A minus equals to 1.25 HA. Does that make sense?
Yes.
Okay. So now, this is actually not 100% correct, but if I erase the bottom one, so like I said, the concentration of A minus plus the concentration of HA should be equals to 0.1, equals to 0.1 molar. Okay. Make sense?
Yes. I see now.
Yeah, so where you get this is you just replace A minus concentration with 1.5 HA, which you got from here. So that will give you the concentration of HA. Should be very easy. And after that, you just replace the HA value into this equation. You can get the value of A minus concentration. Okay.
Thank you. That makes sense now.
Cool.
So is there supposed to be 2 HA? So the 1.25 HA plus HA?
You mean here?
Yes.
You mean you're supposed to be or what? I'm sorry.
Is there supposed to be the 2 HAs? So the 1.25 HA plus HA?
Yes, because 1.5 HA is come from here. It equals to A minus.
Oh, okay, I get it. Thank you.
So HA is from here. Okay. Any more questions? If no more, I will let him start. And while he is doing the calculations, I will probably explain more detail because I think he probably will have the same questions as you guys may have. Okay. So I think now you can start. So first of all, you start with your calculation. What I want from your side is for method 1, you told me the mass of HA, the mass of weak acid you need, and the volume of strong base you need. And the same thing for method 2. So for method 3, just let me know the mass for weak base and weak acid. Okay, so the stock solution for strong base and strong acid are both 1 molar. We are providing 1 molar stock solution for you. So you just need to tell me. You just need to tell me what the volume for this. For weak strong base and strong acid. Okay, so you can get started. Let me know if you have any questions. Sure, I will enable share screen. Now I will stop sharing, and I will let him sharing. Let him share his. Let him share his screen. Okay, now I think now you can log into the Zoom and share your screen.
So do you have your volume on? In that case, I'll just turn mine off and so we'll start. So do you have your volume on right there?
I use mine. I will mute myself.
Okay.
So.
Okay, do you hear me?
Yeah, we do.
Oh yeah, I can hear you.
So I'm gonna go to. All right, so we're doing number 1 first, where we're doing a weak acid and a strong base. Is my screen sharing all right? All right. So. Just gonna note down what we're doing first. So this is H2. Here 4. And we do a H minus. Then we said we had 1 molar sodium hydroxide. And did we say we had 0.1 molar for potassium phosphoric acid or whatever? Right. So I guess we figure out how much moles we have. So how many liters did we say we had? 5 milliliters or
50 mil.
50 mil? 5 liter. So I'm just gonna change colors here. So we have a 0.1 mole liter times 0.5 liter. It's gonna be 0.005 moles. So just to be clear, so our like the phosphoric acid thing, that's gonna be the powder, right?
Yes.
So we're gonna need that thing's mass.
Yes. Actually, if you look at here, that is the molecular weight.
So we have that, and then we have also just gonna write K for short because I'm not lazy to write the whole thing out again. But potassium phosphate dibasic. So when we're saying dibasic, is it the deprotonated form or?
So dibasic means it has 2 potassium here.
I see.
That will be your weak base. So your weak acid will be mono acid.
Alright, so we're looking at the mono acid guy then, which is gonna be 136.09 grams per mole. For total mass, it would be mass would be 0.05 mole, 136 grams per mole.
Liang, quick question. Are you gonna post this recording?
Yes.
Okay, thank you.
I believe it's something like this. No, it should be. Someone confirm if that's correct and tell me. I just quickly did that in my head.
Yeah, that's correct.
That number is correct.
Right, so that's our mass height. And I guess we want to know how much volume of sodium hydroxide we want on top of that. So again, so for each liter of sodium hydroxide, we have 1 mole, which is gonna be, and we're gonna cancel out that with 0.005 moles. So we want so I guess we want 0.005 liters or 5 milliliters of NaOH.
No, that's not what you mean.
Mhm.
So next step you need to do is you do the calculation of this one. So
All right, you gave us a pH.
right, yeah, you do this.
My bad. So, all right. We want to. So we have a pH. We have a pK. We have plus log. What is it? A minus. Yeah, I'm just. We have all of these guys. So we said this is 7.3. We said pKa is a 7.2. Plus, I'm not gonna write that out again. Sorry. So we have a right 10 to the point 1, which I think would be someone calculate that and tell me what the number is. More interactive that way, so I'm too lazy to get a calculator.
That's 1.25.
Someone say an answer. I'll put it in the Zoom chat. It's 1.25. Thank you. So that's 1.25. So we're saying so. Yeah, we have A minus equals 1.25 HA. And then, we know the original concentration is supposed to add up to, or I guess at least the original number of moles. Should be how many moles do we say again? 0.005 moles. In this case, I'm just kind of taking concentration as just the moles for shorthanding it, because the volume would technically increase and things would get diluted, but yeah. So we'd have something like this, and then we said that it's 1.25 HA, so we could just say it's 2.25.
So wait a second. So the HA concentration plus A minus concentration should equal to 0.1 mole, so which is here.
Right, but you know, if you're technically adding a liquid, right, wouldn't it get diluted?
What?
Like since we're technically adding some volume to it, right, through the base, wouldn't the concentration technically decrease a bit just because the volume's increasing?
It will not. So think about it. Initially, you are adding 0.1 molar of this. Okay. So after you add this, the concentration of that will decrease, but you will get more of this.
But like, yeah,
So
that's
the,
like
so the sum of this and this will always be 0.1.
yeah, I'm using the moles because like you see the volume itself changes, right? Like it's moles over volume, so moles is conserved, but if we look at the volume, it technically increases a bit, so the sum would technically be a bit less than 0.1. You see what I'm saying? And it's a very small change, but you know, I'm kind of trying to take that into account.
No, actually,
It stays the same, and even if it's a very small change, it's negligible enough that we don't need it. It's fine.
it will not be any changes even you add the acid or base into it. The reason is so like I said, the step of making the buffer is we measure the powder, we add the strong base or acid, then we add water, but we are not adding 50 ml of the water. We just add water, bring the volume to 50.
All right, so we're
So
actually
we are not changing
okay.
the volume by adding this.
Okay, I get that. Okay, that makes more sense. Thank you. All right, so we said 0.1 mole, 0.1 molarity. Yeah. I'm just making sure I have everything understood right. Like 2.25 of the protonated acid. The 0.1 m, and someone tell me what happens when I divide 0.1 by 2.25. 0.04. Thank you. And someone tell me what happens when I multiply. Oh, like actually, I can figure that one out myself. So, because it's the remaining part. It should be 0.06 m. 0.44, 0.56. Okay, that's probably better to use a bit more suffix then.
Yeah, I think the answer in the chat is correct. Yeah.
So we have this amount of things, and yeah, so I'm gonna so like what's a wage gave us A minus kind of, right? So just by approximation, so we're saying this is 0.044, this is 0.056, and we started off. So we should start off where we started. So we started off with 0.1 mole. So my Apple Pen's acting a bit weird, right? And then we subtracted 0.056 moles from it, right? So we used up whatever we have. We used up 0.56 moles. Yes. We 0.56. So we need X itself to be 0.056 to cancel it out, maybe, right? So we're saying six. And so is sodium hydroxide also a powder, and we have to make that solution, or
It's the stock solution is 1 molar.
So we'll just need to dilute it, I guess.
Yes.
So we are adding 0.56 molar in can use the C1V1 C2V2 equation. About how we're okay, we're gonna put all our things in the same beaker or something, right? Yes. So if you are using C1V1 equals to C2V2, so the C1 will be 1 molar. So V1 is what you want to know. C2 is what you have here, 0.056, and V2 is 15 mil. 15 mil. So 15 mil is just the volume of our of the things we have in the beaker. That's even. Okay. Yeah, that's what I was doing. So it's at 0.1 molar times however many volume equals 0.056 times 15 milliliters. So I guess that's just so no more units, the units cancel out. Someone do this calculation and tell me, sorry, that's so sweet. Someone tell me how many milliliters this is. It's 2.8. 2.8. 0.8 milliliters. Okay. So yeah, I guess we. This is not 15. It's supposed to be 50. 50. Okay. Okay, that makes more sense. Yes, I misheard that. Okay, there you go. Okay, that is basically for your master one. Should it be 28 mil or 2.8? 2.8. All right, 2.8 mil. All right, so I guess we can start now. I think you can do all the calculations for these 3 steps. Okay, yeah. Start making them. Okay, part 1. I'll quickly run through part 2. That's pretty much the same thing, I guess. Part 2, we have and it's the same pH and pKa, I assume. Same pH, 7.3. Yes, same pH. Right. So yeah, so we have 0.1 molar of it. So that's gonna be a 0.1 is that 10 milliliters or so I forgot what milliliters we used last time. What? How much volume we have for same thing here. Right. I kind of forgot what we call 50. Yeah, sorry. So it's a 50. So sorry. So it's gonna be 50 mole. Right. So we have 0.1 mole per liter. That's 4.5 liters times 174 grams per mole. Go ahead and do the calculation. I'll put it in. It should be 0.87 probably, something like that. I'll do it myself, 0.445. So I guess it should be point.
Why did you do 0.05 instead of 0.1 liter in that equation?
Oh, I did that because it's 50 milliliters for the solution, so it's 0.5 liters here. Yes, that's correct. Right, okay, so I'm having a hard time doing this in my head. 0.74. Maybe not divided by 5, so we should have like it's like 0.87 mole. Am I completely off? Or
That's correct.
so that's the first thing we need to know. That's how many. Sorry, not mole. That's grams. That's right. Oops. Yeah. So that's grams. Second thing we want to do is figure out the ratios, right? So we kind of have the same thing again, where like pH equals pK plus log. And we already did a lot of it, so like we know that A minus equals 1.25 HA, right? From last time, so 2.25 HA equals the total concentration. Well, I guess nothing actually changed, huh? So I guess the numbers would be the same. Numbers would actually exactly be the same. So that's that. And I guess we have the same HCl concentration. This should be, I guess I should use C instead of N. It should be 0.056. No, this time it will be 0.044 if you look at the equation, right? Because we're using up the base this time of the acid. So it should be 0.056 molarity, and then we said, or sorry, was it last time? It should be 0.044, right? And I guess if we do the calculations, this should give us 2.2 this time, 2.2 liters, right? And for part 3, I guess we'll use a different color. Green's nice. So we have weak base plus weak acid. So I guess we're literally just inflating the concentrations and nothing else, or do we have to do anything else?
So for the third line, you just use the concentration you get from here times the volume,
Right,
which is 50 ml, and times the molecular weight. That gives you mass.
Oh, right. So we literally just artificially make it. Okay. Yeah. So yeah, as far as I remember, we had we had all of this good stuff. Small, and we just multiply it by the volume, which is 50 milliliters, which would give us so it's 0.6. This would be 2.8 mole. This guys, and for 2.2 moles, this guy we have so HA, that would be 136 grams per mole. And this guy we have 174 grams per mole. Someone multiply all of these guys and give me the answer, because yeah. 0.87 grams for what? Oh, I might have missed a decimal place. That's my bad. I multiplied by milliliters instead of liters, so it's actually like point. Yeah, sorry, that's kind of my bad. But yeah, I just need to divide by 1,000, so your answers are correct. The first one's 0.299 grams. And what about the second one? All right, 482, thank you. yeah, that's all we need, I guess.
Leanne, can you check that? Because I kind of used it.
Correct.
Oh, okay.
Just a second, let me check the answer sheet. I think the number looks right. Yes, that's correct. Yep.
That's good. I'll
You're ready.
let me stop share. Okay, so I've also can you guys hear me still? I can stop my sharing. All right, so I'm gonna put a link for the spreadsheet I'm gonna put my data on, because I think that might be more helpful to keep it interactive or whatnot. So yeah, it's like copy pasting.
Well, you can email me that spreadsheet and I will send it everybody.
You know, I put it in the Discord chat. If anyone's in the Discord chat, could you like copy paste it in? It's kind of hard to copy paste in an iPad Zoom. 1.4872. That's a small difference. It's fine. But yeah, if someone could like just go to the Discord chat and like copy paste the link, I'd be extremely grateful.
You mean Discord?
Yeah, I put the link in Discord a bit earlier.
Well, I personally can't use Discord because I think ASU has some like policy with that. So if you guys want to do that, that's fine. But I'm not allowed to.
Oops.
Yeah,
Yeah, so
like I said, you can just email
I'll
me.
just email it to you.
And I can share it with everybody.
Yeah, I'll just share it with you, and then I can go ahead and share it with everyone. Because like copy pasting an iPad's just weird. Can you put your email here? Yeah.
Well, you can do. You can start work on your experiment now.
Before I get some gloves.
Yes. Okay. My email is here. I can mute her. You can mute herself. Then I can unmute myself. It's not very.
I shared it with you. You can go ahead and like share the link with everyone in the chat.
Now I will start to film you.
Basic one, I believe.
Yes. You just weight this on the weight bolt, and you just grab 3 beakers from the rack. This is you make the buffer in the beaker.
Beaker.
Yes.
And yeah, do I need to do anything in the fume hood? I know.
No,
like
that's why it's pretty.
Because it has some strange.
That's fine. Yeah, that's why it's fine. I think these beakers are too big for you. Yeah, you just need to make 50 ml. So these are about 250. So if you look at the side, the level of your solution will be too low. And when we are measuring the actual pH after this, you need to make sure the pH meter, the probe of the pH meter is covered better. That one looks better. Okay. You just close it.
That's my bad.
All right, it's working now.
So that's zeroed out.
Yes.
This guy here. We got 0.68 grams, which is 68 milligrams or 68 milligrams, yes. 68 milligrams. So it is
No, we have the spoon spatula here.
so like this.
Yes. Okay, let's keep my use this one to clean it.
I wouldn't recommend putting it back in. It's gonna create impurities.
Exactly. So we don't recommend you put this back into your weight bowl because these are not clean anymore.
Oh, yeah, that's fair.
Yeah.
Just we'll have to get rid of a bit of it anyways. So, do we have anywhere we can do some mixture?
You can pour it here.
So how many sig figs do we want? Just two sig figs that we're buying, as you need.
What mass you are measuring? You are rating?
So we're looking for 680. So I'm assuming
Okay.
anything that's like accurate to 2 sig figs is fine.
Yeah. Try your best.
Yeah, right. Get it closer.
That's too much.
Barely added anything.
So let me show you how to get this. So beware the cloth. Can I have the spatula? This. So when you are getting close, sometimes. Yes. So it's still more than what you need. You need 680, right?
Yeah, 680.
Okay, now it's 666. So sometimes when you are getting very close to your desired number, you just get some of the powder, hold with your right hand, then you just put your just gently push your right hand like this, so you can get things get closer and closer. So now you have 680.
Oh, that's nice.
That's how you measure
Yeah, in
the
my
mass.
high school chemistry lab, they just let us. do things
Well,
like that.
sometimes you don't have to be super specific, but for in some case you do need to keep your mass. I mean, more specific the better. So
So I assume
you put it in your beaker, yes. Yeah, you'd better label it, or as long as you can remember what it is.
Is it like OSHA regulation to like label all your beakers and stuff?
Oh, I don't have a marker for this, but
That's fair. Don't worry, I won't drag to OSHA. It's fine. See, so we gotta put water in it until
you put your base or acid in it. Yes, it's right here. So just grab one set of the pipettes from the drawer, and I will bring the acid and base to you. So you just grab one, you just grab the whole box. Yes. And you need the pipette tips over there. No, it's right here in these drawers. You grab one box from each drawer, so 3 different sizes. And on the bottom, on the middle, this one, the green one. And one and on the bottom. Okay. Okay, that's all you need. Since you didn't do in person for lab 1, are you sure you know how to use pipettes or not?
let me just experiment around with it a bit first, I guess.
Yeah, I mean, I can watch you. If you have any mistake, I will point it out.
I don't think I could do it, right? It's just turning it on.
Yes.
Milliliters.
Yes. So first the question, which pipette you are using?
How much does this damage? Okay. 100 to 1,000 microliters. That's not what we want.
Well, you need to use that because this is the biggest one. You just pipette 3 times.
3 times?
Yeah,
Oh, yeah, right. 1,000 microliters.
it's 1 mil.
Liter. That's
Yeah.
right. So my brain got focused on that. So yeah, that.
Yes. And this is the buffer. This is the strong acid and strong base you need.
We calibrate this before we get the pipette.
You don't calibrate it. You don't have to.
You know, we like change.
Oh yeah. So what is the volume right now? It's 1,000.
100. Oh, I guess that's exactly what we need, right?
You pipette twice, so you get 2 mil. Then you adjust the volume to 800, then pipette one more time. That will give you 2.8.
And also, since we're using it for the same solution, do we need to change the pipette?
No.
Right. Where's our?
It's right here. So this is the strong base, and this is strong acid.
I'm kind of notorious for squealing in strong acids and bases in chemistry labs. So we just put it in and just plunge it.
You push it first. You feel the stop. Okay. Yes. Then release it slowly. Well, not that slow, but yeah. Then push it. Do you feel the first stop? Then push further. Okay. Yeah. But don't too deep. No. Just to make sure the tip is beyond the solution is fine. You don't need to push your pipette to the very bottom.
Because now we need to make it 800 or so how much did you say?
800.
How do we change this thing?
You just scroll it counterclockwise. So now do you see here? You unlock the knob, right? You push this one to the from here to here.
Oh, I see.
Yes, now it's 800.
Because 800, I don't think you guys can see it. But yeah. I guess we lock it again.
Yes.
Like, doesn't change.
Mm-hmm.
We toss this away. I mean, we'll be using the exact same solution again, right? So do we toss the pipette away or?
Or have you finished the 800?
Yeah, I have.
So you just toss it away.
I mean, we'll be using more sodium hydroxide. Will we? I guess we won't. Okay, yeah.
You won't. I mean, the tips are cheap, so you don't have to worry about like wasting too many tips, but because it's
Okay, so that's because we need to react with the air.
so now you just start add water in it.
Until 50.
You are not measuring the volume by the line of the beaker. What you need to do is you add let's say about 40 add the water to about 40 ml on the beaker that you can read. Then you use the glasses stir bar to dissolve all the powder in the solution. Then you pour all the solutions in a graduated cylinder to measure the volume. Then bring the volume to 50.
I see. So we just add up and you have distilled water somewhere.
You can just use the water from here, but make sure the pressure is pretty high. So use the red one, left one. Like I said, the pressure is pretty high, so make sure you hold it tight. I guess you have to remake it.
That is high pressure.
Like I said 1 second ago, the pressure is pretty high.
So when you said high pressure, I can actually think that.
It's pretty high. I mean, I think you have to remake it because you spilled like too much. So I just suggest you grab another beaker, collect some water, then you pour it from that beaker.
Yeah, that's my bad. I didn't really explain.
Yeah, no worries. That it happens. no, you pour it to the film hood. Or you can just leave it here. You pour everything in the very end, just grab a new beaker, then restart it.
Yeah, because we barely had any sodium hydroxide, so it should be fine, right?
Well, you'd better pour it in the waste, the liquid waste.
Yeah, that's fair.
I mean, you can leave it here because you need to clean up in the end of the lab. So you just grab a new one and redo from the very beginning.
Well, I can test out my new folding skills, I guess. Zero that out. I'm gonna do it a bit differently this time, just to make sure.
This time I can get a bigger beaker because you need to use the water vast enough to that buffer. That's work.
I'm just gonna, just to make sure there's no high pressure spillage again. Let's go.
Okay. So you pour it to about 40. Then you mix it, stir it with a stir bar. Okay, that's enough. So now you stir it with the stir bar and measure the volume of this graduate cylinder.
Bit left. There goes. Might be hard. There you go. That's dissolved.
Okay.
So we need to
Let's grab a graduate cylinder over there.
this guy.
Pour it into the graduate cylinder. You can do it here.
I'll do it with this.
Okay, so what's the volume now?
That is about 33 milliliters.
Now you bring the volume to 50.
50. So I think this is what. No, that's not what I use for water, is it? This is what I use for water, right?
Yes.
Yeah, because that seems a bit dirty.
It's from the bottom or inside of the beaker.
It's fine, I guess, right? So, right. So pour until 50. All right. It's about 49. It's fine.
Yeah. I think that's
About 50.
now just pour it back to the beaker. That's for your first buffer.
So that's our strong acid solution or weak acid solution.
I'll do your second one.
So and we just want to add sodium hydroxide to it and do that one first, or
You prepare 3 buffers first.
okay.
Then you measure the pH. Then you test the capacity.
That makes sense. We do second guy. Use the dye basic 0.87 grams of the dye basic. Looks like barely anything left in here.
What?
I think we could just finish now. Looks like here. Okay. We'll use this guy first. It's taking so long, it's harder to code than it looks, I guess. Diagonal 870.
Okay. I am measured acid.
gonna do this twice with 1 milliliter, then do a singular point later on. Let's do change.
I'll do the same thing. Add water, dissolve.
Dissolve. Dissolved. Let's go here. So that's the strong base, that's a strong acid. Yeah. Spill, but it looks like the not at all, so it's fine, I guess.
Not too much.
Yeah, it's not too much. It's like it's still around 50.
So
Final
third one.
So it's a 0.299 grams of the acid and 0.487 grams of the base. Okay. So start with the base first. Can I get another thing? So there you go, that's close, 487. We need 0.299 grams of 299 milligrams. Nine. Because you put them in the same beaker, right?
Yes.
We just put water in.
Yes.
Mixes. You'll be done with part one in like 10 or 20 minutes, right?
What?
I think you'll be done with part one in like 10 or 20 minutes, right? Because we're almost done with this part.
Yes.
And then we have to do a part two, right? To figure out the pK2.
Part two basically you just add strong base and strong acid in two of the buffer. Then you measure the pH again. That's it.
Right, yeah. So what do say we have like half an hour, a bit more than that left today?
It depends. It really depends on your.
I've been fair. I've been a bit slow.
It should be quick. The measurement of pH is pretty fast.
I believe we're done preparing the buffers.
Yes.
Strong acid and weak acid plus base.
So next step is measuring the pH, the actual pH value for this. Okay, so this is the pH meter. So how do we use that? So this one is the panel. Basically, there's a very tiny screen which shows the pH. This is the pH probe, the pH meter probe. Do you mute yourself or turn down your volume, because I think it's.
Oh, yeah, might be feedback.
So the pH meter, how to use that? So the pH probe is actually always is soaked in the saturated potassium chloride solution. So the purpose is for protecting the probe. So every time before we use the pH meter, you need to take this probe out of the potassium chloride buffer. And if you notice, there are some like solutions on the probe. So that's why we need to use the squeeze bottle, which has distilled water to wash. I'm not sure if you guys can see it, but a little bit. So you use the squeeze bottle to wash it. Make sure you rinse it with a lot of water to get rid of all the potassium chloride on it. Then after that, you use the clean wipe to wipe all the water left on the probe. Okay. After that, you just grab one of your buffer you made, and you put your solution in the buffer, and you record the pH value here. Okay. So it's your turn.
Right. So the pH is a 7.1.
Okay. Record that number, and you do the rest of the measurements. Okay, hold it. Hold it. Okay.
So I guess we're gonna complete it again.
Yes.
Was it fine or?
You just wash it, wipe it with the clean wipe. So think about it. If you don't wipe it, there are still
Right.
a couple drops of the water on it. And when you dip it into your buffer, you dilute your buffer.
That's fair. Wouldn't like molecules of the wipe get attached here? Like,
That's why we use Kim Wipe, so it's fiber free.
oh, that's nice. A science brand, I see. So, do it in the second one, which is the strong acid.
Give it further.
Just hold
Okay. How does you read the number? Record the number.
7.05. I'm gonna go ahead and put that in. The last one is the weak acid plus base, number 3. Okay, that's 7.09.
Right. Okay. So the second part is you never put the probe in the waste bottle because it's quite dirty.
That's true.
If you don't use that, you clean it, wipe it, then put it back into the protection.
We're gonna use it again though, right?
Yes, but you can hang it in the air, but you don't dip it in the waste.
Right. Yeah, so something like this.
Yeah.
Okay.
That works.
Just gonna clean it up again.
You clean it up first. So the second part is you just pick up 2 of the buffers you just made, and for one of them, you add 500 microliters of the strong acid. Then you stir it, measure the pH. For another one, you add 500 microliters of the strong base. Stir it, measure the pH, and that will be it.
So, right, okay. So this guy's the weak acid plus weak base combination. I'll be using these 2 guys since that guy had a bit of a split, which might confound the data. So 1 and 3. And so you want me to put 500 microliter of the acid and the base in one and the other, right?
One with acid, the other one with base.
These 2 guys.
Keeps out there. Tips. Okay, right.
So it's real quick. This guy measures up to 1,000, right?
Yes.
So this part, if I do 050, that would be
Okay.
all right. So I'm gonna put acid in 1. I'm just gonna write the data down first. The acid in the solution, the biggest buffered solution, I guess.
You have already added base in it or not?
This one's the one I made with the base buffer.
Okay, I'll just add whatever you want. Choose one of them.
Just not doing it again, just in case. .93.
Okay.
Did someone record the pHs?
I will sum up. I will collect the data and send it to you when it's done.
Oh, okay. Thank you.
Yeah, putting it in a spreadsheet, so you can share that with you guys. So that's done. Now we have this guy. .34.
Okay. Now you clean this.
I believe we're done, right?
Yes.
Is there a
Right here.
that's nice.
Scroll it.
What liquid's in it? Is it something to keep it clean? Or
It's saturated potassium chloride solution to protect the product.
I see.
Okay. Now you clean the things up and you're good to go.
So where's the waste beaker?
We have a waste container in the film hood. You just pour everything liquid, all the liquid into it. It's right here. So while I'm cleaning, I will collect his data and share to you after this. Other than that, any questions?
Thank you.
Okay, if no more questions, I will see you guys next week. Bye guys, thank you guys. Bye.